the
Hopefully.
Arbogast. Yeah.
All right, David. Thank you for the nice introduction. I want to welcome everyone here to this lecture, the Town and Gown series that Dr. John Waller has organized and put on for the benefit of a lot of different people. It's a very popular series, that covers a variety of topics. I participated a couple of years ago when I was talking about Michigan sand dunes, and John asked me if I'd be willing to talk about the glaciation of Michigan, and I'm happy to do that. But this is only one of many different presentations that you guys will have with a very, very wide range of topics. So kudos to Dr. Waller for pulling it together. We're just kind of a strange time, obviously, and you're kind of getting a feel here for what it's like to teach in a Zoom environment. In the present time, the university's kind of locked down a little bit because of the uptick in the Omicron variant, and people are back to working like this in the classroom. It can be sort of stressful, and it's sort of intense in its own way, and you lack the interaction that everybody craves at times like this. On the positive side, though, people from all over the place can participate in classes and lectures like these from all sorts of places around the country. My own mother is here, quote unquote, here, and she lives in Topeka, Kansas, where I grew up. So this is in that regard, this is a good way to communicate. So first of all, before we get into the whole topic of glaciation of Michigan, I want to talk for a moment about Greenland. This is a typical image of the Greenland ice sheet. Notice all the crevasses and the wide expanse of ice. I bring this up now because we know that ice sheets are cover Greenland and Antarctica, but once upon a time, the Midwest U.S., including all of Michigan, looked like this at some point in time, and dominated the landscape evolution of the region. I'm a geomorphologist. I study landscapes and how they evolve. And I think in terms of stream processes and the kinds of sediments that they carry, obviously along Lake Michigan, we have wonderful sand dunes that are blown and shaped by the wind. Those are fantastic landforms, and they're certainly worthy of study. I do it myself. But the glaciation of Michigan is the dominant process by which the Michigan landscape is shaped. So as we kind of work through this presentation, sort of keep this image of Greenland in mind, because it must have looked something very much like this not all that long in the distant past. So here is a sort of a typical image of what's referred to by people who work with the glacial history as the last glacial maximum. And it, for those in the know, it represents a specific interval of time when during the most recent glacial period, ice reached its furthest extent. And that occurred sometime between 20 and 18,000 years ago. And as you can see, this is a view straight down on the North Pole. Glacial ice covered Greenland, of course, at that time, as it still does, and half of North America, all of Canada for the most part, and much of the northern tier of the United States. Ice also extended into northern Europe and across Russia. So Michigan is located very much on the edge of this. And even though we're a long ways away from the source and the main body of ice, the impacts on the Michigan landscape have been profound, and you can see them clearly if you just know what you're looking for. Another view of the last glacial maximum. Again, this is about 20,000 years ago. Here looking dead on to what's referred to as the Laurentide ice sheet. The Laurentide ice sheet was the largest glacier in North America. It was centered in northeastern Kansas, approximately where Hudson Bay is now. And it spread from that center, both south, west, and east, as you can see by the flow arrows on the image. Now, East Lansing is here. Again, when you look at it in the context of the overall ice sheet and its gargantuan extent, we're really kind of on the fringes of the Laurentide ice sheet. But again, the effects were profound. Off to the west, this feature out here is referred to as the Cordilleran ice sheet. In other words, the mountain system that developed because of air flowing off of the Pacific Ocean and getting caught up in the alpine ranges of British Columbia and southern Alaska. During the glacial maximum, the last glacial maximum, the Laurentide ice sheet and the Cordilleran ice sheet had each spread so far that they joined. But of course, as deglaciation occurred, the famous ice-free corridor, which you might have heard about, developed between those two ice sheets. And it was through that gap that developed that the peopling of North America, the original peopling of North America occurred, both from indigenous people crossing over from Asia on the Bering Land Bridge and coming down the ice-free corridor. And there's some current thinking that they were also moving along the shoreline of North America on the Pacific coast. These people were the famous Clovis mammoth hunters of the time. And I mean, you can only imagine in your mind's eye what it must have been like to hunt one of these things. These sorts of finds have been found in Michigan, including the projectile points and mastodon and whatnot. So there's no doubt that it happened, and it had to do with the spreading of the ice mass and the gap that formed in between them. So back to the Laurentide ice sheet here. This is an isopack map. In other words, what it's looking at is the thickness of the ice. From the center of the ice, which again is over Hudson's Bay, which is right there, to the very edge of the ice mass. Now, this is all in metric, so this is 3,800 meters here and 3,000 there, but to give you some sense of that in the way we normally think around here, at the center of the ice, it was about 2.4, 2.5 miles thick. From the ground level straight up about 2.5 miles. So imagine what that would be like. And then it spread in sort of a dome shape from that location to the edge of the ice mass. Now, on the fringe of it, this is kind of a fun graphic because it gives you a sense of how thick the ice was, even though it was on the margin of the ice, how thick the ice was during the last glacial maximum with cities that we're very familiar with. At Toronto, the ice was about 2.1 kilometers thick. Chicago was buried under about 900 meters of ice, or 2,500 feet, something like that, a half a mile thick. Boston, 1,200 meters of ice, and Montreal, they would have been locked in the deep freeze for sure at 3,300 meters of ice. So when I talk about this in class, I talk to students about, this very place. I'm sitting in East Lansing right now. The ice was on the order of, 3/4 of a mile to a mile thick for a long time, for over 6,000 years. And that's just really impressive. And the impact that had on the landscape is really profound. So again, looking at the dome of the ice mass, and what I want to do now is I want to focus on the Great Lakes region and the glaciation and deglaciation of our homeland here, and the impact that had on the landscape in ways that you can really see. Now, I want you to think a little bit about how the ice flowed into the region. Again, it begins to form in northeastern Canada, Hudson's Bay. And the way glaciers work is that snow accumulates over the course of time. If all of the snow melts during the wintertime, in the summertime, then the raw material for a glacier doesn't exist, because it's just like, I'm looking at a skiff of snow right now. It might be a couple of inches. And if that snow melts in the summer, then we start from scratch. And the process happens all over again. But if the summer is cold, imagine a cold summer in which the snow doesn't melt, then what happens is that the snow accumulates on a seasonal basis every year, and it begins to pile up with maybe a little bit of melting during the summertime, but not all the way down or not all the way gone. And the snow is gradually transformed, kind of goes through a metamorphosis into glacial ice. And when the ice reaches a thickness of about 900 to 1,000 feet, something like that, maybe a little bit more, it can begin to flow under its own weight in a sort of a plastic form. Now, this doesn't happen fast. It's very slow. A fast moving glacier is one that's moving on the order of 3 or 4 feet a year, maybe 5. surging one is 10. And so we're not talking about the Indianapolis Speedway here. This is the kind of thing that takes a lot of time to happen. And for the last glacial episode that we're looking at, it's on the order of about 50,000 years. As it took that long for snow to begin to build, it transforms into ice and gradually begins to flow into the Great Lakes region. I want you to also see in this image, in purple is the last ice sheet. That's the extent of the Laurentide ice sheet during the most recent glaciation, but there are older glacial deposits south of that. And there are even glacial deposits as far as northeastern Kansas, where I'm from. My grandparents' farm, they had a little dairy farm north of Topeka. And there were glacial rocks that were brought to that location during an earlier period of time than the most recent glacial. And that's one of the kinds of things that got me interested in this kind of work, is like, how is that possible that glacier ice made it all the way far as south as northeastern Kansas? Now, the traditional glacial theory was that there were 4 continental glaciations. I guess it was sort of assumed that, this isn't the kind of thing that can happen very often, because, I mean, just think about it. The first glacial period, epoch, if you will, in this 4-stage model, was the so-called Nebraskan glacial. And it was actually referred to as the Nebraskan glacial. And that's because there were specific glacial deposits found in eastern Nebraska that were deposited by ice. And that's on the order of 1.2 million years old. This is the so-called Kansan glacial, which occurred about 600,000 years ago. And that's the ice that reached the most southerly extent in North America. Again, to my grandparents' farm, even. The outline of the Missouri River in the United States really pretty much follows the outline of the Kansan glacial. And that was the stream ancestrally that formed during that time. The Illinoisan glacial occurred about 135,000 years ago. And the Wisconsin glacial is the most recent one, the last glacial maximum, again, between 20 and 18,000 years ago. And this was after about 50,000 years of ice moving into the region very slowly. All right, that was the traditional model. Now, the ice core research that's been done, and there's been a lot of it, tell us something else, however. And the basis for this is that glacial ice, snow accumulates in annual layers that can be identified, sort of like a tree ring. And these ice layers contain microscopic bubbles, air bubbles, that are little snapshots, little slivers of the atmosphere at that time. And isotope analysis tells us it's complicated and it goes beyond what I'm talking about here, but the isotopic signature in the ice bubbles of the oxygen tells us something about whether it was warm or cold during those intervals, which then can be calculated into glaciers and interglacials. And so we know from that ice core data that there have been maybe 18 to 20 major glaciations during the last 2.5 million years, something like that. And the interglacials are time when it was warmer, of course. And so there have been cycles of glaciation and interglaciation, many of them, that have occurred during what's called the Pleistocene epoch in the last 2.5 million years. Now, the older glacial deposits have largely been destroyed where they've been recovered or eroded. So it's kind of hard to reconstruct exactly what the extent of those glacials were, but we know that it happened based on the ice core data. So this is the ice core, the isotopic signature for the past 120,000 years. At the top 10,000 years, the past 10,000 years is referred to as the Holocene. That's the period of time which is sort of coincides with the rise of humans. Of course, we can talk about whether there's an Anthropocene or not, and when does the starting point for that period of time. Here's the last glaciation, the so-called Wisconsin glacial, which is isotopic stage 2. And you can see from 70,000 years ago, which is about the beginning of the onset of the Wisconsin, to 20,000 years ago, that's about 50,000 years. That's how long the glacial epoch took to come to its full flower, so to speak. Stage 3 is the last interglacial period, and that was right after the so-called Illinoisan glacial. So we're very confident in that this history of glaciation and interglaciation has occurred. And what we are looking at in Michigan, the dominant remnants of are the Wisconsin glacial, which is isotopic stage 2. So this animation shows, I like this because it shows what the deglaciation of all of North America looked like in the last 20,000 years. The timestamp at the lower left, Ka, is thousands of years ago. Pink is the ice, and you can see the melting of the ice, so to speak, in the last 20,000 years. Here we go. And notice that there are large lakes that develop in front of those from the ice as it melts, including our own Great Lakes. But all of the lakes that arc up into northwestern Canada is too, such as Great Slave Lake and Bear Lake and those kinds of lakes. One of the most often asked questions is, why did this happen? I mean, how is it possible that we can have so much ice accumulate and grow to the point where Michigan is covered for 6,000 or 7,000 years, and then it all melts away? Sort of an eternal winter summer sort of a thing, but on a very large scale. Well, a German mathematician by the name of Milankovitch is famous for working this out, and he didn't even study glaciers. But what he did is he looked at the mathematics of the orbital parameters of Earth as it goes around the sun. And he accurately concluded that there are 3 different phases to our orbital plane. One is the eccentricity of the orbit. Right now, our orbit is sort of elliptical. That's the current orbit here, which is elliptical, but that's not always the case. Through time, it changes and becomes a little more round. And so the position of Earth relative to the sun is either farther away or closer than it is presently. That works on about 100,000 year cycles. If the Earth happens to be farther away from the sun during the northern hemisphere summer, then we have cooler summers, which means that it's more likely that ice is going to accumulate, grow, and become glacial ice. There's also some variation in the tilt of the Earth. The Earth sort of wobbles through time very slowly on about 40,000 year cycles, with the tilt range moving from about 22.5 degrees at a minimum tilt to 24.5 degrees at maximum tilt. Right now, we're at 23.5 degrees. At 22.5 degrees, if we're also at a point where we're closest or farthest away from the sun during that time, we receive a little less solar radiation in the northern hemisphere, and that allows for cooler summers. There you go. And then finally, the precession of the equinoxes varies over time at about 25,000 year cycles. That means that the summer solstice occurs at one time of the year. Right now it's in June, but it may occur at a different time of year. And this varies over time. And you put all these things together and we wind up with these glacial periods. The last glacial seems to have transpired mostly because the northern hemisphere was tilted towards the sun more, 24.5 degrees, which just allowed just enough radiation to cause the ice sheets to collapse. So what's the impact on of this process, this long-term process on the glaciation of Michigan? Again, we don't really know what happened pre-Wisconsin glacial, because all of those sediments were either buried by additional glacial deposits during the Wisconsin, or they were eroded completely and they've just been wiped off the record. But the most obvious, and for lack of a better way of putting it, the most impressive feature of the Great Lakes region that is related to the legacy of glacial ice are the Great Lakes themselves. And you can really think of those as sort of giant meltwater ponds, if you will, that are legacy of our position on the fringe of the Laurentide ice sheet. Again, here we are. Laurentide ice sheet was the dominant system in North America. Here's our location on the very southern edge. If you look at the ice flow a little more closely, it's moving in from the northeast like so, very slowly over time. Northern Michigan probably was glaciated on the order of maybe 30,000 years ago. And then over the course of the next 10,000 years or so, it advanced to the point where all of Michigan was covered, reaching as far south as central Ohio, central Illinois, and even Indiana. So we were in the deep freeze for 5 or 6, maybe 7,000 years. Now, the formation of the lakes is very closely related to the bedrock geology of Michigan. This is a cross-section of Michigan from west over on the Wisconsin side to east over on the Ohio side, or the Ontario side over there. And I want you to notice that the rock structure, in other words, the layering of the rock and the shape of the rock configuration in that stack of rock, is sort of kind of, it looks like a bowl. In fact, this is the famous geologically Michigan Basin, which contains rock, sandstone, limestones, and shales, soft rocks and hard rocks that date back to, the Cambrian period, other times during the Paleozoic, when the North American continent was tilted radically from what it is now and was south of the equator even. So these were warm seas that accumulated sediment that became rock, and the legacy of that era persists to this day in the formation of the Great Lakes. So again, back to our structural diagram here with the rock units buried but bowed gently. I want you to note that these rock units in the center of Lower Michigan and the UP are harder. They're more resistant to erosion. So as ice moved into the region from the north and the east, these stones, while eroded, were eroded slowly, and they put up resistance to erosion in such a way that the peninsulas of both the upper and lower peninsulas of Michigan were able to kind of hold their own, for lack of a better way of putting it. Now, in the fringes of the Michigan Basin, there is a rock unit that arcs from the east side of the basin, the east side of Lake Huron, over to Green Bay, Wisconsin. This is the famous Door Peninsula. This is extremely hard stone, the Niagara Dolomite, that is a prominent feature in the region. Lakes Michigan and Huron are underlain by relatively softer rock compared to the rocks within the interior of the peninsula and on the fringe. This softer rock was more easily eroded by ice as it advanced into the region from northeastern Canada. The ice first went into those basins where it was easier to erode. And with each successive glaciation that occurred, the ice preferentially went into those places first, dug them out a little bit more, and over time, the net effect is our Great Lakes. But these fringe, these marginal places where this very hard rock that crops out from Green Bay to Georgian Bay in Ontario, if we look at it in map view, the red pattern that you see is this rock unit. Notice that it's in a semicircle, which reflects the fact that this stone, the sediments that became this stone, accumulated in a basin, sort of like a bowl, and a bowl is round. This rock unit holds up the Door Peninsula over on the Wisconsin side. It arcs across into the UP. The chain of islands in the archipelago in northern Lake Huron is part of that rock unit, and then it moves on down into Ontario. If we look in this region here, this shows up beautifully in a Google Earth image with this chain of islands and the Bruce Peninsula over in Ontario. These are all legacy. For somebody like me who's a geographer and into this kind of stuff, this is fascinating because it shows the relationship of both glaciation and the extremely hard stone that the ice flowed over as it moved into the region. It was so hard that the glacier couldn't wipe it out. Once the ice moved into the Lake Huron Basin, where the bedrock is softer, the ice was able to dig out what is now Lake Huron. Each time glaciation occurred, it happened a little bit more, which widened and deepened Lake Huron and Superior, Erie, and Ontario, and Michigan as well. Now, if we travel farther, looking at the Niagara Dolomite to the south and the east, everyone knows that. Show of hands would certainly show that most of us, if not all of us, have been to the famous Niagara Falls, which are held up by this same rock unit. So it's interesting that the rocks at Drummond Island are the same rocks that we find creating the falls at Niagara Falls. And again, part of this big, broad regional pattern of glaciation and variations in bedrock resistance. Again, back to our deglacial story of North America. And again, you can see sort of a prehistoric Lake Michigan and Lake Huron developing. A huge lake developed on the southwest margin of the Laurentide ice sheet as it melted, and that lake is called Glacial Lake Agassiz. Again, you'll see it here, which was the largest of the North American Great Lakes at one point in time. Not very deep, but covered a huge geographical area. This is Glacial Lake Agassiz here. There's been a lot of work that's been done on Glacial Lake Agassiz to understand the effects of water ponding and where the water flowed and what impact that had on climate. Again, you can see this chain of lakes from Ontario all the way up to Lake McConnell and Lake Mackenzie in Western Canada. Glacial Lake Agassiz is this very large lake in the southwest. Interestingly, Glacial Lake Agassiz drained in different directions. At some points in time, it drained to the southeast into the modern Mississippi River system, what's now the modern Mississippi River system. At other times, it drained catastrophically to the east-southeast into Lake Superior. Now, I'm not an expert on Glacial Lake Agassiz at all. I know a few people who are, and they know every stage, every elevation, every outlet. It's the kind of thing they dream about before they go to bed at night. It's pretty arcane in a way, and you really got to get into it to really truly understand it, but it is fascinating. The impact on the landscape, again, was profound. This is an outburst channel on the southern margin of Glacial Lake Agassiz, shows up beautifully in a radar image of the landscape. Similar thing exists flowing into Lake Superior. The impact on the amount of rock that could be transformed during that time is amazing. This is an outcrop, an exposure of Glacial Lake Agassiz outburst deposits. In other words, when the lake began to flow dramatically through a particular outlet, these are the sediments that it was carrying at that time. Look at this boulder over here. We'll enlarge this, and here's the boulder. Three times the size of any person's head. These are huge boulders that weigh an awful lot, and for water to carry them gives you some idea of the discharge and the magnitude of the discharge and how fast the water was moving. It must have been truly catastrophic on a level that it's hard to imagine, quite frankly. The impact on climate is during that time was pretty intense. Focusing on this area here, this period of time is shortly after 13,000 years ago, and Glacial Lake Agassiz discharged catastrophically into Lake Superior. That water ended up flowing into the North Atlantic. That water was so cold that the thinking is that it shut the Gulf Stream down for a period of time during what's referred to as the Younger Dryas climate period. And the global climate during that time, certainly in the Northern Hemisphere, cooled dramatically, very quickly, over a very, very short period of time. And folks who are working on climate change and the amount of ice and meltwater that can be returned into the oceans if Antarctica and specifically Greenland melt in their entirety are concerned, fearful, curious if this process of the Gulf Stream shutting down would occur again. Is the Agassiz Younger Dryas linkage, is that a harbinger for the future? And if that happens, then Northern Europe and England and the UK, where Dr. Waller is from, are going to have very different winters than they do now because it's going to be much, much colder. But back to the deglaciation of Michigan, this is an image that must have been present at some point in time when ice was calving off into the Great Lakes or proglacial lakes within the interior of Michigan. It must have been something to see. It's one of those things that if I could go back in time, if I had a choice to go back in time to if I had 5 different choices, this would be one of them, just to see what the area actually looked like during the deglaciation of Michigan. Before 21,000 years ago, again, we have ice that's moving into the north from the northeast towards the south. It stops in central Indiana, Ohio, and Illinois, and it builds a ridge there, which is called an end moraine. And then the ice begins to retreat from that period of time. And the way it retreated, it didn't melt all the way from Michigan over the course of the next 10,000 years. It was sort of 2 steps forward, 1 step back, 2 steps forward, 1 step back. Ice would retreat to central Michigan, and then it would re-advance, and then it would retreat to northern Michigan, and then it would re-advance, and then it retreated to the northern part of the UP and re-advance. And this sort of stepwise deglaciation have occurred over about 15, 20,000 years, something like that. So I'm going to show you this animation. It's pretty good, from my colleague, Dr. Schetzel. And it shows, generally speaking, the deglaciation of Michigan from 21,000 years ago to the present. It's not intended to be absolutely correct. It's very hard to reconstruct these things. Time is in the top, 17,000 years ago. And you can see that as deglaciation occurs, that ice opens first in the central part of Michigan. And it remains in the Lake Michigan and Lake Huron basins because that's where the deepest places were, where the rock was softest. And you can see that the lakes themselves take on a whole different characteristic. This period of time, for example, at 14,900 years ago, is there's a lake stage in the Lake Michigan basin that people who work on this refer to as Glacial Lake Chicago. And you can actually see the bluff of Glacial Lake Chicago if you're driving to Chicago. And after you make the big turn on 94 to go down towards New Buffalo, you can see a bluff on the western side of the highway. That is the bluff from Glacial Lake Chicago. At the same time, a lake formed in front of what's the Saginaw Lobe. It's called Glacial Lake Saginaw. No shock there. That lake drained across the central part of Michigan into Glacial Lake Chicago. If you go past Uncle John's cider mill and the Maple River Valley, that huge wetland up there, that is legacy of this flow pattern across the peninsula. So you're going to see that the shape of the Great Lakes and their extent and coverage will vary pretty dramatically over the next 4,000 years. See the ice re-advanced at 13,000 years ago, and now it's melting up in northern Canada, or excuse me, northern UP. This period of time is really interesting because about 11,000 years ago, something like that, the Great Lakes were at their lowest stage. This is called the Chippewa stage of Lake Michigan, where it didn't even fill the basin that we have presently. The same thing over on the Huron side. This is called the Stanley Basin. The nomenclature, the names, the dates, the elevations, all of these things are very, very complicated. I remember writing a paper about this in my PhD program at Kansas. I had no idea that I was going to wind up here, but I just wanted to learn more about it. And it is, quite frankly, it's sort of mind-numbing. I'm giving you the highlights at best. If you really want to get into it, let me know and I'll send you some places, and be prepared to bog down in spots. So that gives you a sense of the glacial deglaciation history of the state. One place where this shows up really well that you all might be familiar with is the northern part of lower Michigan. We could talk about the southeast, the west, the southern part of lower Michigan, the UP, the Saginaw lowlands, all these places, and spend 3 hours doing it. But for the purposes of this discussion, north central Michigan sort of provides a good test case. This area is referred to as the north central interlobate area. It was between the two lobes of the Saginaw lobe, which was to the east, and the Lake Michigan lobe, which was to the west. Sediment moved from the Lake Michigan lobe into the interior. Sediment moved from the Saginaw lobe west into the interior, and it piled up in the central part of northern lower Michigan. In this region here, this is the great up north country that people like to visit so much. And it's so pretty because of this large scale process. In a big view, this is the effect that the glacial history had on the state. This is the pre-glacial topography. This is the bedrock topography of lower Michigan before it was glaciated. South is to the left, north is to the right. We're looking down the axis of Saginaw Bay here towards sort of the southwest. And at this period of time, before glaciation occurred, this would have been like 3-4 million years ago, the highest part of the landscape, the hilliest part of the landscape, was in southern lower Michigan. This would have been the up north country of that time. But because of the effects of glaciation and deposition in the north central interlobate area and places like that, the topography was inverted. There was so much deposition in the northern part of lower Michigan because of the way the ice slopes were working relative to one another that it inverted the topography, so the hilliest part of the state is now in the north. Think about that for a minute. That's impressive. There's on the order of about 2,000 feet of glacial sediment in that part of the state. That is absolutely amazing. It's just incredible. And you can see it as you're driving north. You kind of, just after you pass Clare, you kind of drive up onto this ramp. Notice that the next time you do that, you'll see a gradual incline. You're driving up into that area that was between the two ice slopes. Now, that's the big picture. Smaller scale, the kind of thing that you see, you can actually see on the landscape. In front of the ice, there were landforms such as moraines and eskers and kettle lakes and outwash plains that formed. Kettle Lake is a depression that was created because a block of ice fell off the front of the glacier, kind of like that image that I showed you earlier. It was buried by sediment, and the ice melts over about 1,000 years or something like that, leaving a lake behind. All of the lakes that you find up in northern lower, those beautiful lakes up there, are kettle lakes. The moraines are large ridges that were built where that was the front of the ice for a period of time. And it was acting sort of like a bulldozer that was carrying sediment forward and building this ridge. Outwash plains are places where streams were flowing out in front of the ice, something like this. This is actually from an alpine setting in Alaska, but the same process occurred in Michigan, only on a much bigger scale. Glacier here, this kind of hummocky, rough-looking terrain is glacial sediment that was deposited directly by the ice. Streams are flowing out in front of the ice, and they're carrying sediment, and they have a tendency to build a very flat plain. Now, this all worked out. I know I just went from an alpine glacier to a picture of deforestation, but this was originally worked out back in the late 1890s, early part of the 20th century, when geologists of the time, were taking advantage of the fact that Michigan was pretty much deforested. The trees were cut down. And so because of that, you could see the landscape and where the hills and valleys were clearly. I grew up working on the plains where you can see forever out there. In Michigan, that's not the case. But because of deforestation at that time, I guess the positive from it, if you can think of it that way, is the fact that the glacial history was tackled for the first time. And quite frankly, a lot of that stuff still holds up even to this day, 120 years later. But again, back to our big picture. Here's the geography of prominent end moraines. These ridges were formed when the ice re-advanced into the region. You can see the complexity of the Michigan landscape through this superficial geology map. Blue is lake sediment. You can see lake sediment you can find almost in the center part of Michigan because of the Saginaw lobe. Pink is outwash. Green is direct glacial sediment. Larger scale, the big flat surfaces in northwestern lower are big outwash plains, and green is glacial sediment that was deposited directly by the ice. You can see these things clearly as you're driving through the area. For example, this is the famous Port Huron moraine that arcs all across the northern part of lower Michigan, from the west side all the way over to Port Huron. The Mansalona outwash plain is in front of it. just like the picture that I showed you of the actual glacier in the alpine setting. One interesting thing to think about the next time you are up in this part of the state is that the ice, the top of the ice had to be at least to the top of the ridge that you see. So that gives you some sense of the magnitude, the thickness of the ice, and just how impressive the whole thing was. And all of that ice is gone now. It's really pretty impressive. Now, of course, what makes that part of the state so beautiful is because it's a great place to hike and camp, play golf. I love to play golf, and the golf courses up there. Well, let me tell you, let me put it this way. When I'm playing golf up there, I think to myself, I'm not in Kansas anymore, because there's nothing in my home state, as much as I love it, that looks anything like this. And this is all the legacy of glacial ice. Or if you like to ski at Nubbs Knob or Boyne Highlands or any of those places, that is legacy of the glacial ice. And this image, I like this because it gives you some sense of the thickness of the ice right here in Michigan, because it had to be at least as thick from the skier in the pink to the cabins down below. And if you drive around the northern part of Michigan thinking about that, I'm willing to bet that you'll be kind of blown away. So with that, I'll leave it. We could spend a lot of time talking about the glacial history of the state. I just touched on it briefly, kind of hard to get through it in 45 minutes, if I even made that. And I want to thank everybody for their time. Of course, I'm willing to stick around and happy to answer any questions if you have.
Thank you so much, Dr. Arbogast. That was very informative. And I'm also from Kansas, so it was interesting to learn that glacier ice extended that far south, because that's something I never would have thought occurred. If you're all right, we're going to open it for a period of question and answer. There's kind of three ways people can ask questions. The first is they can use the reaction function to raise hand, and I'll just call on you and you can ask your question out loud. Secondly, you can type question in the chat, and again, I can make reference to that, and then you can ask it out loud. Or if you'd prefer not to unmute yourself, you can just write the question in the chat, and then I can ask it for you. So those are kind of the three ways we're going to do questions. It looks like Stan has a question, so we'll let him take it away.
So,
all right, Stan, fire away.
Okay, so I heard you attribute the changing climate over time to changes in the Earth's orbit.
Yep.
Years ago, I was visiting the Peabody Museum in Harvard, and they had an extensive exhibit on how the climate has changed, and they attributed it to changing carbon dioxide levels in the atmosphere. So what would you say about that?
Yeah, okay, so that's a really good point. It's the reference that I was making about climate change with respect to glaciation is that the orbital parameters and how much radiation is received in the northern hemisphere is what governs, generally speaking, what governs the advance or retreat of continental ice sheets on that kind of a scale. And that certainly seems to have something to do with it. The ice core data also shows that there is a linkage, there's some kind of relationship between those cycles and the CO2 cycle that you just mentioned, and that there is some kind of relationship there as well. That certainly has relevance in the here and now, because the impact of atmospheric loading of CO2 is moving into this big climate change cycle that we're in right now. When I speak to people who talk about, well, climate change occurred in the past, you've just proved that or talked about it under so-called natural circumstances. Why can't we assume that's going to happen in the future? And obviously, to some extent, it will. The difference is that the kind of climate change that occurred over the Younger Dryas that I referred to, that was about 12,000 years ago, that was over the course of several hundred years. That was fast. The advance of glacier ice took 50,000 years. That was fast. Even the deglaciation of the Great Lakes region took 10,000 years. And that's geologically fast as well. The kind of things that we see now are happening on the order of decades. So long-winded answer to say you're absolutely right. CO2 has something to do with it, but the orbital parameters do too, at least as far as the melting and the advance of the ice. Good question, though.
Thank you.
Question. I'm an upstate New Yorker. I grew up in the Finger Lakes areas and drumlins.
Yes.
You mentioned drumlins. I assume from my geology class at Cornell that the Finger Lakes were river valleys and they were carved out by the glaciers. So they made them just big lakes. And the drumlins were just cases where the ice rolled over and dropped its load. So they run north and south, but they just ran over the top, you might say. Does that differ from Michigan?
It's the same. It's when you think about upstate New York and Michigan, we're the history of landform evolution is very, very similar. Excuse me. The Finger Lakes, as I understand it, having talked to a couple of people from around there who've done some work there, the Finger Lakes are sort of very, very small scale versions of our Great Lakes, in the sense that in those lakes, where those lakes are now, the bedrock was a little softer. And there were stream valleys that were present because of that relationship. Just as the thinking is that before the Great Lakes were present, there were stream valleys that would have occupied where the lakes are now. And when the ice advanced into northwestern New York, it preferentially eroded those softer stream valleys that pre-existed, forming the Finger Lakes. Again, a smaller scale version of the Great Lakes, really. As far as drumlins are concerned, they're interesting because they're actually shaped by the ice in sort of a plastic way. As I understand it, and again, I'm not a glaciologist, I know just enough about this to be dangerous. The sediment is there previously, and the ice overrides it, and in so doing, it streamlines it. The compression forces of the ice flowing over the mound of pre-existing sediment streamlines the feature. If you look at them from plan view from above, they're kind of teardrop shaped, with the point on the downstream side of the ice and the blunter end up at the upstream side, and that it's sort of behaving in a plastic way as the ice flows over it. But yeah, there are nice drumlins in Northwest Lower. There are great drumlins in Wisconsin, and of course, where you're talking about is sort of ground zero for fantastic drumlins.
Thank you.
I grew up in Cincinnati and was taught in grade school. The Ohio River was the melting of the glacier. But were you saying that there was some glacier in Kentucky, say, and did they melt and flow north or down to the Tennessee River or what?
Yeah, well, let me back up here. I assume everybody still can see this. It'd be better if I pulled up a map of, okay, let's go here. All right, imagine in your mind's eye where the Ohio River is. It would flow, just about where the 80-degree west longitude is, flowing to the south and the west. And the Missouri River, which originates in the Rockies, flows towards the south and east. The Missouri River and the Ohio River, as my understanding of it, certainly the Missouri River, is that they are legacy of the ultimate, the maximum glacial advance in North America. And that was during the so-called Kansan glaciation. I'm not just plugging Kansas because that's where I'm from, nor because my mother's here, but because the ice, that northeastern Kansas is as far south as the ice reached. And in the process of doing that, the meltwater streams that flowed in front of it were the ancestral Missouri and the ancestral Ohio rivers. So in that sense, it is related to the deglaciation of Ohio, but probably at an earlier time. Ice in the most recent glacial maximum did not reach the Ohio River per se, but certainly meltwater from the ice in northern Ohio would have flowed into the Ohio River and had some impact that way.
The other thing is, I sort of vaguely remember being taught there were four glaciations or whatever. And were you saying that basically the detail of the geology is less well known because of the last melding wiped out so much?
Yes, sir. And that's a good point. There are glacial sediments in northeastern Kansas. I've seen them. They're very heavily eroded because they were deposited so long ago. Whereas glacial deposits cover literally all of Michigan, or most of it anyway, that's because the most recent glaciation only occurred, in East Lansing. East Lansing was on the ice margin 16,000 years ago. That's nothing. So those glacial deposits are very fresh and they haven't been weathered much. In northeastern Kansas, on the other hand, it's been 600,000 years. Now, there are some boulders that are in northeastern Kansas. It's a pink boulder, kind of a quartzite, that crops out in Minnesota naturally. And those litter the ground in northeastern Kansas, where the ice came. It carried this rock is just, it's so hard. And ice ripped up the boulders from southwestern Minnesota, carried them to northeastern Kansas and dropped them, and they're still present today, and you can see them everywhere.
And one final question, and I'll shut up, is what is the prediction from the Earth wobble and orbit as to when the next ice age will occur?
Yeah, I don't know about, off the top of my head, I don't know about where we stand with respect to our orbital shape and the precession of the equinoxes, but I do know that, on the order of 12,000 years ago, we were at our maximum tilt, which is 24.5 degrees. Now we're at 23.5. And we're slowly, very slowly moving to our minimum tilt, which of course will take, another 20,000 years or something along those lines. And when we get to that point, I don't think you and I need to worry about it. We will be at our minimum tilt in the northern hemisphere if it happens to be occurring at the time of the year when our summer season is, when we're farthest away from the sun. Then we'll receive even less radiation, and so that could be the onset of a glacial, right? There are some who think that the ultimate impact of climate change, ongoing climate change, could be, ironically, another glacial interval, because if the North Atlantic is inundated with cold water from the Greenland ice cap, then the Gulf Stream, which warms Northern Europe, will shut down, and who knows what happens at that point.
Great. Yep. Go ahead.
I've got a couple of questions. I'm not Denise, I'm Tom, her husband. Continuing with the change in the Earth's orbit around the sun and the precession and so forth, I assume those factors are involved in the advances and retreats over the deglaciation period that you were talking about, or something
Yes.
caused them anyway. What's the explanation for that? And then I've got another question.
What's the explanation for why the Earth's orbital parameters vary over time?
No. You were talking about during deglaciation, there are the two steps back, one step forward kind of kind of thing where you would get a lot of melting, but then it looked like refreezing or re-advance. I was thinking
Yeah.
that must have something to do with these cycles of variation you were talking about in the orbit and so forth, but I don't know. So I was
Yeah,
wondering,
no, I don't believe they do. There, I mean, there's the big picture, which the orbital parameters, and again, CO2, that is part of the story. The big picture of the continental ice mass advancing and retreating as a whole is related to those kinds of things. But what's going on in Michigan with respect to the advance, retreat, and then re-advance and retreat, and those kinds of things, that's more, again, as I understand it, more of a sub-regional response to the ice sheet mechanics themselves. And that's not really related to the big picture specifically. For example, there is a boy, I wish I had time to, I'm starting to get fired up now, but there was a lobe of ice that advanced from northern Minnesota to Des Moines. This lobe of ice is called the Des Moines lobe, and I'm sure you could find it on Google. The Des Moines lobe was as ice was retreating from Michigan, from the Great Lakes region, the Des Moines lobe suddenly surged. And by surged, the estimates that I've seen is like, 100 feet over 10 years. It's not something you need to run away from. Let's put it that way. But still, that is surging. And it's to the point where it reached Des Moines. As you drive west on 80, as you approach Des Moines, you actually drive up on that lobe. And that has something to do with the fact that there was so much meltwater, maybe related to the glacial lake Agassiz, that the base of the glacier became lubricated. And so it flowed more easily. So it's those kinds of things that are going on that explain, and I'm probably doing a lousy job of this, but that explain kind of the stepwise and sort of uneven deglaciation that occurred.
Yeah, no, I understand. And that might, some of that same sort of plastic stuff that you were talking about with respect to the Finger Lakes probably was that kind of thing.
Right.
The other question I had, it looked like the sort of the furthest advancing lines that you showed us through Ohio and Indiana and Illinois, to some degree sort of trace where you see mound builder civilizations built mounds and left them over. I wonder if there's any relationship there, or if I'm just drawing some bad conclusion here. Playing association or something.
Yeah, you're right about the sort of the relationship, at least in terms of geography. But the mound builders were much later. I mean, that's a boy, I got a little bit of archeology in me.
Well, no, it is a whole lot later. I know that, but I was wondering if there was something about the terrain that was left, or the kinds of soils and rocks that were in there and so forth that were conducive to that kind of architectural thing. It just occurred to me to wonder.
Yeah, it would be pure speculation on my part.
Yeah. Okay. Yeah. Thank you.
Yep.
Sue had a question in the chat. She asked, what's the relationship between the glaciers and the good soil in southeastern Michigan, so like east and south of East Lansing, if there is one?
Yeah, that's a good question. It's you can think of glaciers. Well, let's jump really far abroad, and to Australia. Okay, Australia, might have been glaciated in the ancient past, but that in many ways, Australia is such a deeply weathered place because it's remote, and the effects of continental glaciation, are so long ago, if any, maybe in the Blue Mountains and those kinds of places, that all of the soils and the sediments are so eroded that they're very infertile. On the other end of the spectrum is the Midwestern United States. The Midwest is very fertile in stark contrast because largely because of the effects of glaciation. If you drive across northern Illinois, for example, much of the state is covered by what's called loess. That's spelled Loess. And loess is windblown sediment, windblown silt. Much of Nebraska, virtually all of Iowa, Illinois, Indiana, those kinds of places are covered by loess to a great deal. That sediment blew out of the Mississippi and Missouri River valleys because those streams were loaded with glacial meltwater sediment. And as those streams dried a little on a seasonal basis, whatnot, that dust would blow out of the river valley, cover the landscape, and it is very, very fertile. The ice itself, in mixing the sediment and depositing new sediment here and there and other places, had the same effect in sort of rejuvenating the landscape fertility, if you want to look at it that way. The Saginaw lowland, Midland, St. John's, those kinds of towns, that flat part of the state that is otherwise sort of featureless is very fertile because it was under the pro-glacial Lake Saginaw. And that sort of fertilized the landscape, so to speak, created this flat plain that's easy to farm. A similar sort of landscape exists in the southeastern part of Michigan that was related to pro-glacial Lake Erie and all of its different configurations. And so the process of glaciation, directly or indirectly, has had a huge impact on the overall fertility of the Midwest.
Sue was also wondering if glaciation had anything to do with why northern Ohio, so like south and east of Toledo, is very flat.
Yes, absolutely. Because that was on this image that I have up right now. I assume everybody can still see it with the position of the end moraine and the last glacial maximum. Look at Lake Erie right here. Southeastern part of southeast of Toledo. This is a big lake plain from the different stages of glacial Lake Erie. The modern configuration of the Great Lakes as we know them now is only about 2,000 years old, maybe 2,400 years old. As you could see from the animation that I showed, let's see, where are we here? This animation that I showed, the lake shapes varied dramatically over the course of time. And there was, just as we had glacial Lake Chicago in the Lake Michigan Basin and pro-glacial Lake Saginaw on the Saginaw lowland, this map isn't going to get us to Lake Erie. The similar sort of history exists for Lake Erie. There you have lake names like Glacial Lake Whittlesey. You can kind of get a sense of it here as the ice was retreating from the Erie Basin. Here's southeastern Michigan, this very flat landscape is legacy of that. And that exists all the way over into northwestern Ohio, which is why that topography is so flat. Good question. Anybody else? Obviously, I could talk about this all night long.
Denise asked, could you suggest books or articles to learn more about this?
Yeah, there's a really good book that I would recommend. It was edited by a good friend of mine, Randy Schetzel. He actually built this animation. Randy is a professor in the same department that I'm in. We're very good friends. And it's called The Geography and Geology of Michigan. And his last name is spelled Scheetzl, Schetzel. I have a chapter in that book about Michigan sand dunes. I think the book was published in 2009 or something like that. But it will give you a very good overview, first of all, of the fascinating geography and geology of Michigan as a whole, which is very interesting. But there's a deep focus on the glacial history of the state because it's had such a profound impact on the region. So again, the geography and geology of Michigan, edited by Randy Schetzel. That would be a great book.
I believe Dr. Waller had a question.
John.
This is Sandy, not John. Can you describe how the underwater aquifers were formed? You talked about surface water and surface conditions, but how about below the surface?
Well, yeah, that's a really good question. Now, you can think of the aquifers as being regional features in some ways, but kind of local features, depending upon if there is porous sediment that overlies impermeable sediment, and so that impermeable sediment, maybe a clay, something like that, holds that water up locally. That effect occurs all over Michigan. On a regional scale, the ice, there was so much sand and gravel that was deposited by the ice that it makes a fantastic aquifer. Again, I'm not an expert on Michigan's aquifers. I know the High Plains aquifer very well because, that's where I'm from, and it remains in the news to this day. But on a general level, Michigan's aquifer system is tied largely to the copious amounts of sand and gravel that were deposited by the ice. Those deposits are very porous. Obviously, we receive a lot of precipitation over the course of the year here in Michigan. The aquifers are recharged on a regular basis. The evidence for those is everywhere. The streams such as the Manistee and the Muskegon and the Ausable are fed by groundwater for the most part, where those slopes intersect the water table. The glacial legacy is really pretty impressive in that regard. Most of the mapping these days is related to determining the thickness of those kinds of sediments and their suitability for aquifers. It makes a lot of sense. Anybody else? My fellow cans in here. And I'm not referring to my mom.
I don't believe so. That doesn't look like it. Well, thank you so much, Dr. Arbogast. This has been amazing. I think Dr. Waller wanted to say some final remarks, but I'll say thank you to everyone for coming. This has been really informative.
Well, it's been a pleasure. I always enjoy talking to these groups, and obviously these are easy things to talk about because it's so cool.
Alan, that was incredibly enjoyable. Thank you so much. I love hearing about, as you kept using the word magnitude. Just the vastness of these processes is absolutely awe-inspiring. That was a really wonderful presentation. So thanks for giving up part of your evening for this. I want to acknowledge David Costa, who is new to Town, and I didn't realize, partly because he's so polished. This is David's first time moderating a Town and Gown, and David is a second year in the Scholars Program. So I'm hoping that we'll see a lot more of David over the coming weeks. I did notice there may be another question from Carol.
Did I miss something about the sand sculptures on the beaches?
I didn't talk about that, but we can talk about it briefly if you want.
I'm curious.
Yeah, I got a couple of calls from the press about that. And it was fascinating. I had never actually seen them myself. I don't know if you probably saw the same picture I did. That image makes them look like they're pretty tall, maybe 5, 6, maybe 10 feet tall. They were on the order of about 4 inches to a foot in reality. So they were actually quite small. But it's I'm pretty sure what happened in that situation is that you have a frozen beach. It is wintertime after all. The beach is frozen. There was a big storm that rolled through a couple of weeks ago. I don't know if you remember that, but there were straight line winds over on the lakeshore that were 70 miles an hour, gusting to at times. That's almost near hurricane speed. And those strong winds scour the beach. Now, in some places, the beach is frozen a little more than other places. Who knows why? A little more water, I don't know. But in the places where the those sculptures that you see that were present for a brief period of time, they were the more, I'm speculating that they were the more frozen areas, and the softer areas were blown away, leaving the more frozen areas behind. It's kind of like it's the same story as the Dore Peninsula, is that rock layer was so hard that the Dore Peninsula is what's left. But and the wind and the sand blowing across the beach scoured out the softer areas, quote, less frozen, and it sort of sandblasted the other parts that were more frozen, creating those kind of weird shapes. Interestingly, they're very similar to bedrock features like that are called ventifacts. That's spelled VENTIFACT if you're curious. And you can look up images of ventifacts. They're most common in the United States and the Southwest. And you'll see a lot of the same sort of features, kind of these streamlined rock features that look not as cool as what you saw along the lakeshore, but still reminiscent of that.
Thank you.
Yep, you bet. Dr. Waller, I have no doubt that the reason why David did such a good job is because, he's a native Kansan.
But you're not in Kansas anymore.
Yeah, but it never leaves, does it, David? No. And I'm about to go watch my Jayhawks play basketball right now, as soon as we're done here. So that's just not the kind of thing that goes away.
Well, just one last thing from me before Alan, you can go and fulfill that wish. Next week we'll be joined by Dr. Nigel Paneth, who is a very accomplished Michigan State pediatrician and epidemiologist who spent a lifetime working on neurodevelopmental disorders among children, but he's also recently been doing important work related to COVID. So please come back, same place, same time next Tuesday. Again, thanks so much, Alan, and David too.
All right. Well, thanks everybody for joining me. I really appreciate your time.
Thank you.
Take care.